Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Electrolyte Materials for Redox Flow Batteries, Aqueous Electrolyte from paper Energy Related Materials. So students, let us see what are we going to discuss or learn in this module. From this module, you may get to know about the following points. First, the role of aqueous electrolyte materials in RFPs. Second, types of aqueous electrolyte materials. Lastly, about the working mechanism of various aqueous electrolytes in RFPs. So let us start with some introduction about the aqueous RFPs. According to the phases of electroactive species, RFP may be classified into three groups, such as first, all liquid phases RFPs, where chemical energy is stored in the electrolyte. Second, all solid phases, where chemical energy is stored in an active material on the electrolyte plates. And the third one is hybrid redox flow batteries. In liquid phase RFPs, both the redox couples have reactants or products dissolved in the liquid electrolytes, whereas in solid phase RFPs, both the redox couples, including the solid species, while the charge process. In hybrid RFP systems, one of the redox couples involves the solid species or gaseous species at 1/2 cell during the whole charging process. Types of RFPs based on all liquid phase aqueous electrolyte materials. The EES capacity can be enhanced by utilizing a large amount of electrolytes, as the chemical energy is stored in the electrolyte materials. All such batteries need ion exchange membranes, that is IEM, separating the anode and the cathode compartments, but allowing the transport of ions to maintain the electrical neutrality in the cell. Iron chromium RFP. This is the first type of RFP which we will be discussing. Modern development in RFPs started with the development of iron chromium in the 1970s at NASA. A schematic of iron chromium RFP has been shown in the figure below. The iron chromium systems were designed and demonstrated with a capacity of 1 kilowatt 13 kilowatt hour for a photovoltaic array application. This system is based upon an aqueous solution of a ferric or ferrous, that is Fe2 plus or Fe3 plus redox couple as positive reactants, and the mixture of chromic and chromous ions or Cr2 plus or Cr3 plus as negative reactants respectively. However, most systems use hydrochloric acid as the supporting electrolyte, iron chromium RFP system can function with an IEM and low-cost carbon felt electrodes. For both reactants, the charge transfer reactions involve only one electron transfer, which shorten the charge transfer and result in reasonable surface over potentials without using electrocatalyst. It is a known fact that iron redox couple is highly reversible on carbon or graphite electrodes. However, the chromium redox couple has slower kinetics and hence required electrocatalyst. This RFB system has a comparatively low open circuit potential between 0.9 and 1.2 volts. The design of iron chromium system must withstand crossover of iron to the chromium stream and vice versa. Some companies based in Japan have developed similar batteries by licensing the NASA patents. However, it does not show any significant improvement in the low output voltage and efficiency. The charge transfer reactions at each electrode can be explained as: at positive electrode, Fe2 plus charges or discharges to give Fe3 plus 1 electron, with E0 is equal to plus 0.77 volts versus Rhe. At negative electrode, Cr2 plus charges or discharges to give Cr3 plus 1 electron, with E0 is equal to minus 0.41 volts versus Rhe. The overall reaction now becomes Fe2 plus Cr3 plus charges or discharges to give Fe3 plus Cr2 plus. During charge and discharge process, Cr3 plus is reduced to Cr2 plus at the negative electrode, and Fe2 plus is oxidized to Fe3 plus at the positive electrode respectively. The reverse process can occur while discharge process. An IEM divide the two flowing reactant solutions and stops the cross mixing of the reactive cations. The electrocatalyst used for chromium redox couples must have a high overpotential for hydrogen due to its evolution tends to be a highly competitive reaction during the reduction of Cr3 plus to Cr2 plus. The electrocatalyst used in this system included gold, lead, thallium, and bismuth. The slow kinetics at the chromium electrode caused due to the presence of Cr3 plus complexes such as Cr H2O 6 to the power 3 plus and Cr H2O 5 Cl to the power 2 plus. These complexes showed a slow accomplishment of equilibrium between them. Hence, porous three-dimensional electrodes are being utilized to enhance the reversibility of the chromium redox reactions. These porous electrodes are made out various carbon-based materials such as carbon felt, graphite foam, porous graphite, etc. All vanadium RFP. The vanadium redox flow battery VRFB was first developed by Maria Skylas Kazakos at University of New South Wales in 1986. A schematic of iron chromium RFP has been shown in the figure below. The VRFBs used the same metal in both half cells, that is V2 plus or V3 plus redox couple as negative reactants and V4 plus or V5 plus redox couple as positive reactants. Both redox couples showed significant kinetics in sulfuric acid supporting electrolyte. The IEM or separator is used to achieve the electrical balance via transport of proton across a membrane and dividing the electrolytes within the electrochemical cell. The charge-discharge reactions for VRFP can be explained as follows. At positive electrode, VO2 plus H2O minus 1 electron charges or discharges to give VO2 plus twice of H plus with E naught is equal to plus 1 volt versus SHE. At negative electrode, V3 plus 1 electron charges or discharges to give V2 plus with energy E naught is equal to minus 0.26 V versus SHE. Now the overall reaction will become VO2 plus V3 plus H2O charges or discharges to give VO2 plus V2 plus twice of H plus. The VRFP is successfully worked at a temperature range of 10 to 40 degrees Celsius and it showed good power density values, that is, for example, a cell containing the 1.7 molar vanadium electrode produces power density of about 25 watt-hour per gram. The VRFP showed an open circuit voltage of 1.26 volts. Furthermore, under actual cell conditions, that is 2 molar VOSO4 in 2.5 molar H2SO4 electrolytes, the open circuit potential of the cell is 1.35 volts at 50% state of charge SOC and 1.6 volts in a fully charged state. There are various advantages showed by VRFP such as first, the use of same metal in both half cells and utilizing 4 different oxidation states of vanadium in solution can eliminate the problem of cross-contamination by migration of different redox ions across the membrane. Even if redox species diffused through the membrane, in that case the electrolytes can be reproduced by mixing and then electrolysis without complicated chemical treatment. Second, VRFP does require electrocatalyst for electrode reaction and showed relatively fast kinetics of the redox couples, which provide or allow high charge and voltage efficiencies. The overall energy efficiency of about 70 to 90% has been observed with a 1 kilowatt VRFP stack. Third, it has a very slow rate of gas evolution during the charge rates. Lastly, the overcharged and deeply discharged within can be accomplished within the limits of the capacity of the electrolytes. Furthermore, it can easily be cycled from state of charge and discharge without permanent damage to the cell or electrolytes. Finally, the another advantage is that the electrolytes used in here can be recycled, which leads to a long cycle life and reduces the cost of the system. These advantages makes the VRFP a promising EES technology for large scale storage of energy. Besides these advantages, the VRFP system faces several major challenges, such as low specific energy density in comparison to other EES battery technologies. This lower value of energy density depends on the concentration of vanadium species, which cannot be enhanced due to the precipitation of solid vanadium compounds. If the vanadium concentration increased beyond 2 molar, V2O5 precipitates in the V5 plus electrolyte above 40 degrees Celsius, and solid vanadium oxides participate in V2 plus or V3 plus solution below 10 degrees Celsius. Even with the positive effects of the additives, the vanadium concentration remains limited to below 2 molar for most practical batteries. At this lower concentration, the VRFB system is supposed to be impractical for their applications. The other major challenge is the highly oxidizing nature of V5 plus, which can result in degradation and corrosion of IEM and the positive electrode material. There are only few membranes have been found to have chemical stability in V5 plus solution. Further, the highly oxidative nature of V5 plus limits the selection of the positive electrode material to carbon or graphite felt. These challenges enhances the cost of the VRFP system. Though the VRFP has received the most attention of all RFPs and a number of successful demonstrations are scattered around the world. Other vanadium based RFPs. A VRFP based on vanadium polyhalide flow battery was proposed by Skylis Kazakos to increase the energy density. This system uses VCl2 or VCl3 redox couples, negative reactants, and Br minus, Cl minus or ClBr2 minus redox couples as positive reactants in both the half cells respectively. In this system, the concentration of vanadium ions can be enhanced up to 3 molar, which significantly higher than VRFP, that is maximum of 2 molar. In vanadium polyhalide system, the higher solubility of vanadium avails the energy density up to 50 watt-hour kg. However, this system showed a rapid loss of capacity because of vanadium ion diffusion across the membrane into the positive half cell solution due to large difference in ionic strength between the two half cell solutions. This problem of osmotic pressure can be overcome by adding vanadium bromide to both the half cells, which results in vanadium bromine RFP technology as shown in the figure below. The proposed charge-discharge reactions of V polyhalide redox flow cell can be described as follows. At positive electrode, VCl3 plus 1 electron charges or discharges to give VCl2 plus Cl minus with an energy of E0 is equal to minus 0.05 volts. at negative electrode, twice of Br minus plus Cl minus charges or discharges to give Cl Br2 minus plus twice of an electron with an energy E0 is equal to plus 0.8 volts. A feature of the latter battery is the development of a two-phase electrolyte system. In this system, the bromine complexes separate out into an organic phase while charging, and its stability depends on the temperature and SOC. However, the current complexing agents are very costlier for commercial applications. Hence, commercialization of the vanadium bromine RFP will be ultimately dependent on the successful development of improved and low cost complexing agents. On the other hand, to achieve the higher cell voltage CE3 plus or CE4 plus or Mn3 plus redox couples used as positive reactants and V2 plus or V3 plus redox couples used as negative reactants respectively. This combination results in vanadium cerium and vanadium manganese RFPs. The vanadium cerium RFP has various advantages of high coulombic efficiency of around 87%, high cell voltage of around 1.87 volts, and low self-discharge rate. However, the major issue of the system are the low solubility of cerium sulfate and slow redox kinetics of the CE3 plus or CE4 plus redox couple. Hence, the future research will be focused to develop low cost catalyst and high surface area electrode materials for efficient kinetics of the cerium couple. Similarly, VRFP based on vanadium iron was introduced to reduce the cost of this system by utilizing relatively low cost elements Fe2 plus or Fe3 plus in the positive electrolyte. This system showed improved stability at an elevated temperature and facilitates the use of a low cost membrane. Recent studies demonstrated that V or vanadium and Fe2 plus or Fe3 plus can be mixed together and used as the positive redox couples of a battery, which can effectively increase the energy density by 66% in comparison to typical vanadium iron RFP. Bromine polysulfide RFP. The bromine polysulfide RFP was first demonstrated by Remick, and after that it extensively studied by Regenesis Technologies from 1993 until 2006, since it was developed by VRB Power Systems. A schematic of iron chromium RFP has been shown in the figure below. This system employs sodium bromine NABR electroactive species in positive half cell and Na2S4 electroactive species in negative half cell. While charging of the system, Br minus ions are oxidized to Br2 and complexed as Br3 minus ions at the positive electrode, whereas S4 2 minus ions are reduced to S2 2 minus ions at the negative electrode. Both the half cells are divided by a cation exchange membrane CIM to stop the diffusion of sulfur anions through the membrane, and the electrical balance is acquired by the transport of Na plus ions across the membrane. The proposed charge-discharge reactions of the bromine polysulfide redox flow cell can be described as follows. At positive electrode, 3 Br minus twice of an electron charges or discharges to give Br3 minus with E0 is equal to plus 1.09 volt versus SHE. At negative electrode, Sr4 2 minus plus 2 electrons charges or discharges to give twice of S2 2 minus with E0 is equal to minus 0.265 volts versus SHE. Thus, the overall reaction becomes Sr4 2 minus plus 3 Br minus charges or discharges to give twice of S2 2 minus plus Br3 minus. For the period of discharge process, the sulfide ion acts as reducing agent and the tribromide ion as oxidizing species. In comparison to other bromine-based systems, it does not require any complexing agent. For this system, the open circuit voltage is 1.5 volts at 50% SOC and 1.74 volts in a fully charged state at 25 degrees Celsius in 1 molar NaBr and 2 molar Na2S4 divided by Nephron 125 membrane using graphite as the positive electrode and porous nickel sulfide as the negative electrode. 3 series of bromine polysulfide RFP systems have been developed, including 5, 20, and 100 kilowatt class systems so far. A commercial size system having capacity of about 15 megawatt was successfully demonstrated, which used up to 120 modules and 200 bipolar electrodes with an EES capacity up to 12 megawatt hour and two 1800 meter cube electrolyte storage tanks. Now let us discuss about the all uranium and neptunium RFPs. Two redox couples of uranium and neptunium were used in RFPs, which have remarkable similarities with all the vanadium redox couples. Both the redox couples of uranium and neptunium are in the form of UO2 minus or UO2 minus and NPO2 minus or NPO2 2 plus, which are used as the positive reactants respectively, while the metallic ions of U3 plus or U4 plus and NP3 plus or NP are used as the redox couple in negative reactants respectively. The higher solubility of these redox couples can be achieved by complexing both with the acetyl acetonate in aprotic solvent. A significant quantity of such element can be collected from the nuclear power industry, which can further be used in a flow battery for load leveling applications in a safe and radiation shielded environment. Further, an excellent DC energy efficiency up to 99% has been estimated from mathematical models for such systems. This slide discusses about the operational parameters and performance of all aqueous RFP systems. Liquid electroactive species such as chromium and Cr6 plus or Cr3 plus, Fe3 plus or Fe2 plus, and Ce4 plus or Ce3 plus were studied to have a higher electrochemical rate constants on complexing with triethanolamine TEA, diethylene triamine pentaacetate DTPA, and ethylene diamine tetraacetate EDTA ligands, respectively, which opens the possibility of using certain redox couple combinations in flow batteries such as all chromium, vanadium cerium, and iron bromine systems. So, students, let us summarize what we have learned in this module. Firstly, all liquid phase aqueous flow batteries have been discussed in detail. Secondly, these storage technologies showed various advantages of high density, low cost, significant higher efficiency, etc., and their challenges, their corresponding challenges basically, of lower energy density, membrane degradation problem, and chemical stability. Lastly, vanadium based RFP are supposed to be good candidate for energy storage system by utilizing the same metal in both the half cycle of the device. Also, it does not show a critical problem of electrolyte crossover through the membrane. Thank you.